Welcome back to physics, and today we are welcoming you to kinematics.
Woo!
So, new unit, we've done dynamics, which was all of Newton's laws, and now we're moving into kinematics.
This is kind of unit 2, if you want to call it that. So kinematics is basically a study of motion. It's all the things that we talk about when we're talking about objects moving, accelerating. Everything that we talk about within motion is basically a study of kinematics. Some of these words you should already be familiar with: speed, velocity, distance, displacement. Let's review what the difference between them are. Speed is scalar, meaning it has no direction. It's just how fast are you going. Really, it's how much distance did you cover in a certain amount of time. So the equation for that would be d over t.
Which that is, we didn't look at our reference table too much when we were doing this, but that is on the back of your reference table. So when you go to that last page in your reference table, the first formula under mechanics, which all of this is kind of involved in mechanics.
First one.
So the first one there is v with a bar over it equals d over t.
Now let's talk about what the bar means. It means average. If you just take the total distance that you cover and divide it by the total time, you're going to get an average speed. But that does not mean, or average velocity, that does not mean you're going that speed or that velocity the whole entire time. It's just an average. There is another equation that you can use to find average velocity that's not on the equation, but it's the same equation that you use to find the average of anything. Let's say you had two velocities. You would add them and divide it by 2, and you get average.
Okay, so your average velocity is v1 plus v2 divided by 2. Now this formula is for speed and for velocity. But the difference is that velocity is a vector. So when we go to use this formula, instead of plugging in distance over time for average velocity, we're plugging in displacement over time. Because displacement is a vector. I went back to red. And distance is a scalar.
Okay, now, how are you going to know when it's asking you for a speed or velocity? How are you going to know how to report that number? Do you have to report it as a vector? Do you have to report it as a scalar? The question will tell you. The question will say, what is the velocity of this object? Then you must give a magnitude and a direction. But what if the question just says, what is the magnitude of the velocity? Then all you're really doing is calculating speed, because you're not giving a direction. So it would therefore just be the number, which would be the speed.
Alright. So we are talking about one-dimensional kinematics right now, or 1D kinematics. And this is the study of motion in one dimension. So we are only looking at the x horizontal direction, or we're only looking at the y vertical direction. We're not looking at both of them yet.
Yet is the key word here.
We will.
Talk about Jeffrey. Jeffrey here is a one-dimensional constant velocity car, because he only goes forward. That's it. He doesn't turn, he doesn't go backwards, he doesn't jump up into the air, so therefore he's a one-dimensional constant velocity car. A lot of the examples that we will talk about for the next couple of weeks will be one-dimensional, meaning that a car goes east, a car goes positive x, a car, or a ball flies up into the air and comes back down. Not both. Think about a situation where you could have both. A football player throwing a football has to throw it in the x direction and the y direction at the same exact time. But that's called projectile motion, which is not 1D kinematics. That's the next topic. So for right now, you should only be concerned with one variable, x or y.
So let's talk about our car really quick, and then we'll move into some other situations. So Mr. Petersack quickly said that we have a constant velocity car. So a constant velocity car means that we only have to use this average velocity formula because it's a constant. The velocity is not changing. But we know from talking about forces that that's not always true. Sometimes objects speed up, they slow down, and that force is causing an acceleration which changes our velocity. So we need to look at what happens when we have an acceleration.
So this is a new word for us. Yes, we've talked a little bit about acceleration, but we've never really defined it, and we've never really given you a formula for it. So this is our new variable that we're going to talk about, or our new equation. So acceleration basically is a change in velocity. Now,
And it's technically our rate of change
Right.
of velocity.
so what usually happens in the real world is we use the word acceleration as go faster. So someone could tell you accelerate, and they would be basically telling you go faster. But in this class, it gets a little bit different, where when we say accelerate, well, you should then turn to me and say, well, should I go faster or should I go slower? Because acceleration is really just a rate of change in velocity. It doesn't say positive or negative. It just says change in velocity. So acceleration, then, we should be able to figure out, would be a vector. It has a direction.
And we already know our units for acceleration. We've talked about them as meters per second squared, so we can include that as well.
What that means, though, is really meters per second, okay?
Yeah.
Okay, so let's talk about the equation. Well, if velocity is distance divided by time, and I would want the rate of change of velocity, we would have to take the velocity, or really the change in velocity, and divide it by time.
So here we have acceleration is our change in velocity over time. Now this triangle symbol, we should remember from math and talking about slopes that it means delta or change in. And you should remember that when we're talking about a change in something, so a change in velocity, what we're really doing is our final position minus our initial position, or our initial velocities.
So your final velocity minus your initial velocity.
Which we can kind of replace in here. So I can say that that equals v final minus v initial over time. They're the same formula. So it depends on what kind of information you're given or what you're trying to solve for, what form of this formula we're going to want to use. So this is the first formula on our reference table. And then let's just make sure we're talking about them in the correct order. This is our second formula on our reference table on the back.
So we've changed it in my class. Your second best friend for physics.
What's your first best friend?
Me.
Oh.
So your second best friend being your reference table. Number one, velocity. Number two, acceleration. Okay? Two very important formulas that we're going to be covering a lot in the next couple of weeks and using a lot in the next couple of weeks.
Now, this formula is written in another way right underneath it. Okay?
Third formula on your reference tables.
But it's really the exact same as our second formula. Okay, so if we look at this expanded version, we have A equals VF minus VI over T.
Okay, stop right there for a second. Just going to pause Becker. So, a lot of questions will ask you, what is the object's final velocity? Well, if you start with this equation, or even that equation, it's going to take you a little bit of time to figure out, well, I only want that variable. And you would have to solve for that variable, which we're going to do for you. But if you have to do that very often, why would you keep doing it every single time? So what they've done is, they've done it for you, and they put it on the equation, the reference tables for you. So let's do it once. Now, unpause.
So we're trying to solve for our final velocity. You should remember when we're solving equations, the first thing we have to do is we have to actually just find it, and that's right there. And we're trying to solve for that. Found it. So we have to be careful, because we have VF minus VI, and that entire thing is divided by T. So we can almost put that top part in parentheses. So when we're doing PEMDAS, we're going to deal with that last, because it's in parentheses when we go backwards up PEMDAS, if you remember. So the first thing I need to do is get rid of that fraction. So I can multiply T over to both sides. And I get AT, I'm using my commutative property, just because that's how it's written more often, equals VF minus VI. And then I'm left with that subtraction. So I have to find VF again. That's what I'm solving for. And to get rid of subtraction, I add it. So I'm left with VF equals VI plus AT. And that is equation number 3.
And don't get confused by the part that she wrote AT plus VI. AT plus VI is the same thing as VI plus AT. You should just switch the order, which is fine.
It's just this is how it's written on your reference table, so that's what you should get used to. That's an I. Okay, so we have 3 formulas we're talking about on the back of a reference table right now. Average speed or velocity, d over t. Acceleration, delta v over t. And then these two, remember, are the exact same formula. just written and solved for a different variable. So if you're trying to solve for your acceleration, this is going to be your easier formula to go to. If you're trying to solve for your final velocity, you're going to want to go to number 3.
Okay, so let's do a practice problem. Actually, I'm going to leave you with a practice problem, and you can put your answer into Edpuzzle.
Good idea.
So, let's say we have an object starting from rest. Jeffrey, starting from rest. All of a sudden, accelerates for, let's write this stuff down, accelerates for 10 seconds. Now, it's not going to be real Jeffrey, because Jeffrey doesn't accelerate, he's just constant velocity. But let's say this is another Jeffrey that we have. So, starting from rest, an object accelerates for 10 seconds at a rate of, let's give a weird number, 2.5 meters per second squared.
That's not that weird.
Well, I was just going to use 5, but that's easy math, so 2.5 meters per second squared. Find the final velocity. Let's clarify that. The magnitude of the final velocity. Because if I just said find the final velocity, you would have a problem with that, because I never told you what direction the car was going, and you'd be like, well, I don't know the direction. So now we just say magnitude, which means you only have to give me a number, not a direction.
Okay, so you guys are going to try that, and we are going to continue practicing with these 3 equations, and soon we'll be adding even more. But for right now, we're going to keep practicing with these 3, remembering that 2 of them are basically the exact same equation. If you have questions, please ask. We're always here in the morning. Type them into Edpuzzle, let us know.
And please understand, if you're having problems now, you will continue to have problems until you get those problems fixed. So if you're not understanding this, please show up and let's fix it. Okay? Have a great night.